Morning everybody. Today we are discussing the next topic, that is the hydrides of the oxygen family. We know that the oxygen family have have the element as oxygen, sulfur, selenium, tellurium and polonium, and the physical state of the oxygen family is entirely different. H2O water is exist in the liquid state and H2S is exist in the gaseous state, and all the other H2SC, H2TE, H2PO are poisonous gas. So only H2O is exist in the liquid form. Now we are moving into the structure and hybridization of the hydrides of the oxygen family. As you know that all the molecule are exist in sp3 hybridization. So we know the bond angle of the sp3 hybridization is 109.28 degree. So we are expecting that bond angle to all this molecule, but the bond angle of the water it is 104.45 degree, and for in the case of H2S it is 92.1, and in the case of H2SC it is again reduced to 91, and in H2TE the bond angle is again decreased to 90 degree. So this decrease is mainly due to the presence of the lone pair which is present in the central metal atom, that is the element which is present in the oxygen family. So we know that the repulsion between lone pair is slightly higher than lone pair bond pair and greater than bond pair repulsion. So this is mainly due to the lone pair bond pair repulsion that the bond angle is reduced little bit than that of tetrahedral geometry. Now we are moving into the comparison of the boiling point. The water has high boiling point. The boiling point of the water is 100 degrees Celsius. This is mainly due to the hydrogen bonding existing in the water molecule. Whereas in the case of the H2S, it is reduced to minus 60.31 degrees Celsius. This is mainly due to the as we moving into the H2S, there is no hydrogen bonding is existing in the H2S. That's why the boiling point is reduced. While we are moving from the selenium H2SC and H2TE, again the boiling point is increased. This is mainly due to the van der Waals force of attraction. And now we moving into the some of the oxides of the sulfur. We have to study the two oxides SO2 and SO3. So OSO bond angle in SO2 is 119.5 degree, and SO2 exists in sp2 hybridization. The first one is the ground state of the sulfur. The s orbital is fully filled. P orbital, one of the p orbital is paired, and other remaining other are the half filled, and 3d orbital are empty. But during the excitation, one of the one of the electron in the p orbital is excited into the 3d orbital, and the s orbital and 2 of the p orbital is undergo hybridization, and we will get sp2 hybridized orbital, 3 sp2 hybridized orbital. And this 3 hybridized orbital combine with the oxygen atomic orbital of the oxygen and to form the sigma bond. And there is 2 of the electron, one is present in the 3p orbital and other is present in the 3d orbital, does not undergo the hybridization. These orbital combine with the atomic orbital of the oxygen and to form the pi bond. So it form p pi p pi and d pi p pi bond. So the bond length of this the oxygen and sulfur is 143 picometer. The structure is a planar structure is obtained for the case of triangular planar structure is obtained in the case of the SO2. And next we are moving into the SO3. As in the case of the SO2, the SO3 is also existing in the sp2 hybridization, And the first one is the excited the electronic configuration of the sulfur. The s orbital is half filled and p orbital is again half filled, and 2 of the p orbital in the 3d is also half filled. Then during the hybridization, we will get sp2 hybridization, and 3 of the sp2 hybridized orbital combining with the orbital of the oxygen. And there are 3 orbital which is does not involved in the hybridization. One is in the p orbital and remaining 2 3d orbital, which will undergo the overlapping with the orbital of the oxygen atom and to form the triangular planar geometry. And as in the case of SO2, this hybridization is same and geometry is also same. So the structure in the structure we can again see that p pi bond and p2 p pi d pi bond is also present in the SO3, whereas in the case of SO2 one p pi bond and remaining one p pi d pi bond is existing.